Hello everybody, another edition, another video, and today we're going to be looking at tree diagrams, and we're going to be looking at how we could use conditional probability with the aid of tree diagrams to solve probability questions. Now, so I'm going to dive straight into our first example here. Now, it says 95% of the drivers wear seatbelts. In serious accidents, 60% of the drivers die if they don't wear a seatbelt. 80% of those that wear a seatbelt survive. So we're going to try to represent this information onto a tree diagram. Okay, so I have obviously put up some of the titles here. Okay, we have the seatbelts, we have the outcomes, and we want to count the probabilities. Okay, so we do know that 95% of the drivers wear seatbelts. So I'm going to write here as seatbelts, no seatbelts. Okay, and we do know that 95% of drivers, I do have the tendency to write my probability as a decimal or a fraction. I'll try to avoid using percentage because it does create some kind of a confusion when we do the calculation. So I'm just going to convert this into a decimal, which gives me 0.95, which means that we have 5% of the drivers who don't wear seatbelts. That's going to give me 0.05 here. Now, the outcome, obviously, if you wear a seatbelt, you could either survive or you could die, isn't it? So I'm going to put survive and die, survive and die. Okay, and we put the probabilities on the branches itself. It says that 60% of drivers die if they're not wearing a seatbelt. Okay, so since we have 60% if they don't wear a seatbelt, so we need to look at where is no seatbelt. So we got no seatbelts here, and we do know that 60% of the drivers will die if they don't wear a seatbelt. So this would be basically 0.6, which is 60%. Then obviously we do know that the probability of drivers who survive if they don't wear a seatbelt would be obviously 0.4. All right, if you take 1, subtract 0.6, that should give me 0.4. Now, and we do know that 80% of those that are wearing a seatbelt will survive. So again, this should be 0.8. And obviously we have 20% may possibly die if they wear a seatbelt. Now, one good habit, I would say, when it comes to a tree diagram is to work out the last column, which is the probabilities. Because we do know that if we move along a branch in a tree diagram, for instance, if I want to find out the probability of someone wearing a seatbelt and who survives, we know that we're going to take 0.95, we're going to take this probability, and we're going to multiply this by 0.8 because they are independent events, and if you move along the branches, we multiply the probability. So let's do that now, okay? So we're going to do like probability, seat belts, and who survive. That's going to be 0.95 times 0.8, okay? Then we could obviously do the next one, which is seat belt and die. Then this would be 0.95 times 0.2. All right, I'm just going to do 2 for now, but you get the point, okay? On how this could be very helpful, especially when it comes to calculating the probabilities in this case. Now, so having said this, we're going to start looking at the first question. It says, what is the probability that a driver died? Now, so we need to look at possible outcomes where a driver could die in this scenario. Okay, so if we look at the tree diagram, there is a good chance that he could die if he wear a seatbelt. He could die. Or you could possibly be not wearing a seatbelt, so I'll just call it NSB, which is no seatbelt, and you could also die. All right. Now we do know that the probability of having a seatbelt and die, which is 0.95 times 0.8, and if we put this onto the calculator, that's gonna give me 0.76. Okay, so this would be 0.76. Or we could have another scenario where he is not going to wear a seatbelt and he also may die. So we're going to take 0.05, which is on this branch, and we're going to multiply this by 0.6. And again, if we put that onto the calculator, that should give me 0.03. Now, if I have 0.76 or 0.03, now have a good think about this. Would you add or would you multiply the probabilities? Now, you could have this outcome or another outcome. These are what we call mutually exclusive events. And when that happens, you simply add the two probabilities up together, which gives me 0.79. Okay, again, very straightforward. Again, just trying to use the information given to us on the tree diagram to calculate the probabilities, and it all comes down to understanding between what independent events are and what mutually exclusive events are. Now, what I really want to draw your attention would be part C, and I want you to look very closely how the question is being phrased. Now, it says, what is the probability that a driver who died was not wearing a seatbelt? Now, again, if you read this question again, it says, what is the probability that a driver who died? This was literally a condition that has been set to you in the question. So we are only looking at, instead of looking at all the drivers, we are only looking at drivers who died. Okay? Now, this comes back to what we know about conditional probability. Now, I want to retrace or revisit some of your memories on what we did about conditional probability. Now, previously we talked about conditional probability is that maybe I should start off with a Venn diagram first. I think that would generally be even better if we can start off with a tree diagram. Oops. So let me just take this away. Now, if I got a Venn diagram, okay, so let's say if this is about students who like two different colors, let's call this black, let's call this yellow. Now, so let's say if I have 5 students who like black only, maybe 2 who like black and yellow, and 8 who like yellow only, okay? And my question is, what is the probability that someone likes yellow given that he likes black? All right. Now, so we do know that the condition given in the question is that given that he likes black. So we're not looking at all the students who potentially would like both colors. We are only looking at students who like black only. And if you look at the Venn diagram, we have 5 and we have 2 here. So instead of actually putting this as 15, which is not correct, what we will do is we'll remove this 15 and we will change this to 7, because only 7 people, which is 5 and 2, like black color. And why do we do that? It's because the condition given to you in the question is given that he likes black. So we are only looking at 7 students rather than 15 students, which is adding up all the numbers in the Venn diagram. Now, but then again, if you look at the question, it says someone who likes yellow as well. So we need to find out how many people likes yellow and how many likes black at the same time. So we got 2 in the middle. And that gives me actually 2 out of 7. And this is what we know about conditional probability from a Venn diagram. Now, so I'm going to go back to this question again. Okay? Maybe I just want to add on something. Now, so we do know that a conditional probability, if we start to use some of the notations, is basically, if we write this as in a notation form, this what it means is that what is the probability of A happening given that B occurs. So this one is the condition. But then how do we actually tie this together with what we've done with the Venn diagram. Now we could actually come up with a nice little formula here. Now we could actually have in the denominator to be B, which is the condition given to us. So I'm going to call this the probability of B. And in the numerator, because you need A and B to happen at the same time, and we know that for that to write in mathematical notation, it's going to be A intersect B. Now, this is actually what we call, right, I'm going to change the color here. It's what we call the conditional probability. Okay, so far so good. Yeah. Now this is going to be in your formula booklet, so something that you can always refer to if this is going to be a very difficult formula for you to remember. Now, what I would like to do now is let's do a bit of a let's go back to this question again, and let's see how we can apply this onto this question, and we try to apply the formula as well. Okay, and I'm going to write this in the proper notations so that this will make a bit more sense, and you could actually do a nice application of the formula as well. Now, so what the question is basically saying is, what is the probability that a driver, okay, sorry, I'm just going to erase this again. The probability of a driver not wearing a seatbelt given that a driver died. So essentially what this is what this question is all about. It says, what is the probability that the driver who died? Remember, this is the condition. This is the condition. Okay? And what I want to do is, I want to find out. Now, again, if we look at the formula, which is P, A given B, equal to P, A intersect B, over P intersect B. So what I'm trying to do is I'm trying to find out what is the probability of the driver not wearing seatbelt and died, and this will be over the probability of a driver who died. Okay, because this is the condition here. Now, do we not know what the denominator is? If you look at the previous question, we found that the probability that the driver died was 0.79. So we know that the denominator is going to be 0.79. And what is the numerator that a driver not wearing a seatbelt and die? So let's go back to the tree diagram. So seatbelt and die. So that would be 0.95 and that would be 0.2. So I'm going to multiply these two probabilities together. And all we need to do is just put this onto the calculator, and we're going to get the answer for this. Divide by 0.79. So that's going to give me 19 over 79. I would rather keep this as a fraction. Okay? All right. So that would be how we could use a tree diagram for conditional probability. Okay? So I'm going to show you next another video on how this works in a table, or sometimes what we call a two-way table. All right, so hang in there. I'll show you the next video shortly. Thank you for listening, and I hope you understand this. Let me know if you have any questions. Hope you like this video. If you like it, hit the like button. Thank you very much, guys.